Class, welcome to PEP 288, Motor Learning and Performance with me, Elizabeth Harding. We're going to be going over online learning assessment number 3 regarding the bilateral transfer task that we did the other day and some data that's been provided for you on Learn. So bilateral transfer is also known as cross-education, and it's the phenomena that we see when the training of one limb enhances the skill acquisition of another. And it turns out that this is actually quite beneficial, say for sports performances or even activities of daily living, where we'd like to be able to use both limbs with equal proficiency. So it turns out that the direction of the transfer is important, and we're going to have asymmetric and symmetric transfer. So asymmetric transfer is where you learn the skill with one limb, you really hone in on that motor program, and then start practicing or learn the skill with the other. And then there's symmetric transfer where you learn the skill by practicing with both limbs simultaneously, or maybe one set with the right, one set with the left, and then repeat. As far as which direction of bilateral transfer is better, it turns out that bilateral transfer occurs more frequently with asymmetric transfer. So fine-tuning, really learning that skill with one side and then transferring it to the other. Here's a question for you from your Learn Smart modules regarding limb dominance or limb preference and bilateral transfer. There is sufficient evidence to recommend that for most skill training and rehabilitation situations, the greater amount of bilateral transfer occurs from the what to the what. So I'm going to let you think about that for a second. So according to your textbook, the answer is B. So the greater amount of bilateral transfer occurs from the preferred to the non-preferred limb. Now there is some conflicting evidence as far as different experiments that have actually seen the opposite to be true, where bilateral transfer, the greater amount of bilateral transfer occurs when the non-preferred limb learns a skill and then supposedly teaches the other limb. However, your authors cite a very interesting point about their, their rationale for this response, which is participant or student motivation. So we tend to like to do things that we're successful at, and really to set you up for success, it's probably better to start a skill on the dominant or preferred side. And so motivation certainly plays a factor. And so for this question here, if you were to see this again, say on an exam, the greater amount of bilateral transfer occurs from the preferred to the non-preferred limb. So why does this occur? So there's two explanations. The first is the cognitive explanation. So this is the cognitive aspects of the skill. So the knowing what to do, the rules that we create about that skill. So that cognitive knowledge is what is transferred from the practice limb to the non-practice limb. The next explanation is the motor control explanation. And there's evidence for both the generalized motor program and the dynamical systems theory. So recall from way back, the generalized motor program is essentially that recipe box of movement skills, right? And so proponents of the motor control explanation say that, well, it's actually that generalized motor program that gets transferred from the practiced limb to the non-practiced limb. Then, of course, we also have the dynamical systems theory, which says that all systems, so whether the timing and spatial components of a skill, even pressure, touch, proprioception, all of those are coordination patterns, all of those systems self-organize to find a desirable attractor state. And that's what's transferred from the practice to the non-practice limb. Okay. And then, of course, within motor control, we really have to discuss the role of our central command and interhemispheric transfer between the right and left hemispheres of the brain. And of course, the corpus callosum is predominantly responsible for that. And just so you know, that research does support both explanations. So both the cognitive explanation and the motor control explanation, which does incorporate both the generalized motor program and the dynamical systems theory, even though there are two very distinct schools of thought on both of these. So we did this task here star tracing task where you were supposed to draw or trace within these two barriers, these two orange lines here. And we counted an error as just deviating from that barrier. So I noticed that some of you might have done something like this, right? So we were trying to learn this novel task where you were tracing within the lines by looking into a mirror. And so some of you might have had, you deviated here out of the barrier, and then it was taking you a little bit of time to get back in. And we just decided to count that as one error. Okay, so you deviated here. All of this, even though it did take you a while, that's just going to be reflected in your time score, but we're just counting that as one error. Okay, so here's a deviation, and so you were to sum your errors and then also have someone time you during this task. You were trying to do it as quickly as possible, but with as few errors as possible. And so the score was calculated as 100 over the number of errors plus the time. So the higher the score, the better your performance. So for this lab, we're calculating the percent change. So this is a common calculation that you'll do throughout your academic career as far as pre and post studies, or even working with clients. You want to see their percent change from when they started with you to say when their checkpoint is or when they're about to exit and go out on their own. But we're looking at how much transfer occurred. Okay, so this is we're saying that calculating percent change is the same as calculating how much transfer occurred between your preferred to your non-preferred limb. And this is calculated as the percent change equals your post score minus pre-score divided by your pre-score times 100. And you want to make sure in Excel to make sure that your equation is very tidy and all parentheses are in place so that you get an accurate answer. So let's go ahead and look at your data. So this is what is on Learn. So I went ahead, it's right here. So I went ahead and gave you everything that you needed on one sheet. So I've gone ahead and used the VLOOKUP function for you. So we wouldn't have any of that. So hopefully this was expedited. All right. So for demonstration purposes, I'm just going to cut cut the subject number down a little bit. I think I have, I want to say 13. Yeah, 13 participants. So I have a few questions for you, very easy things that you probably can do very quickly. So I'm not necessarily going to go through that, but questions 1 through 5 were just essentially counting. And then also you'll need to calculate the average age of the participants in your group, which I know that you can all do that. But what we are going to do together is the average percent change for all of the participants in the bilateral transfer task. So here are all of my participants, my 13 participants, and we want to look at the pre-score and the post-score to calculate the percent change. So I'm going to just add a column over here. Okay, percent change, and then typing that formula into Excel. And it might be difficult for you to see here what I'm doing. Oh, doesn't like that. Okay, so you can always look up in the formula bar. So equals post value minus pre-value divided by the pre-value times 100. And I'm going to want to make sure to add all my parentheses. Okay, so I have 158% change. So seems high, but then if I look at my score, my post score was a 2.2, my pre-score was a 0.9, so that's quite an improvement. So that looks about right. And then you can see here, this participant here had a negative 18% change, so they did worse. So just do a quick check, make sure that that looks accurate, and it does. And so we have a couple big scores here as far as percent improvement, or what we would consider how much bilateral transfer actually occurred. So the question was the average. So equals average, and then just take your array here. Okay, and to the nearest whole number, oops, And so I have an average percent change of 46% for all participants in the study from pre to post. So that should get you through at least one of those questions. And as far as the participants that showed the greatest improvement, so this is question number 7. So I want to know if left or right-handed individuals showed the greatest amount of improvement. So what I can do here is I can just make a column for my right-handed individuals and my left-handed individuals. And really what I want is this percent change score. So what I can do is I can do the if function. So equals if. Here's my logical test. So if, go to my handedness, if this cell here equals left, then report my percent change, the value of true. If not, then I want it to report an asterisk or a non-numeric variable. Okay. So I'm just going to format that the same. Okay. So, you see all of my lefties are right here, my righties are right here. My data sheet is actually sorted by left-handed and right-handed individuals. But just good practice using the if function. If, so again, go over here. If this equals, quote, right, then report percent change. If not, then an asterisk. And I just put that asterisk in quotation marks. Okay. And then go ahead and format. Oops, doesn't like that. Okay, so one thing that I do want to share with you, and I've shared in my other videos, but just in case you missed it, is a little nuance in Excel regarding nominal variables. So anything that you give a name to. And it matters how you type it in. So for instance, I have 1, 2, 3, 4, 5, 6 left-handed participants. So you'd hope that if I said count if, parentheses, anything in this array here equals, quote, left, that it would return a value of 6. Well, it returns a value of 0. And so if you can, look very closely up here. Count if, so it looks correct. I have both quotation marks left in quotations. But if you've noticed, well, you can't notice because you can't possibly see anything here. When I entered left, 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 right, 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 I added a space after left before I hit enter. So for instance, watch this number here, and I'm going to delete. If I go left and then hit enter right to the next cell, which I don't get a 0, there we go. So agitating. So sorry about that. So basically I just typed in left and then hit enter and it started counting it. Left, enter, left. Oops, even if I don't count, I don't even have to capitalize, left, enter. So it's starting to count it now. So you can see that what I did here was I actually added a space. So I did left when I originally entered my data. You can see the values going down. So for this, what I want to do is just change my formula to add a space and always make sure that I enter my data correctly. So there we have 6 left-handed participants. This is why this is not necessarily desirable. That it's usually always better to give sort of a numeric value when 1 means yes, 0 means no, or 1 means right, 0 means left. Just to avoid this, especially if you have rows and rows and rows of data. Okay, sorry for the deviation there. Just wanted to clarify in case you're running up against an error over here. All right, so we want to look at the average percent change for our right-handed versus our left-handed. and I can just carry this formula over. I'm just going to round up. So you can see that our right-handed participants in this particular analysis showed the greatest amount of improvement. All right, the next question, I wanted to know if there was a significant difference between the overhead and the non-overhead athletes regarding the change pre to post. So I can do something similar. I'll say OH is overhead and NOH is non-overhead. And then I'll report in their values for percent change. So equals if, parenthesis, this equals 1, then report back their percent change. If not, how about an asterisk? And then if this is non-overhead or 0, then report back their percent change. If not, an asterisk and quotation marks. All right. So one thing that if I were to highlight this and try to manipulate the decimal point by using these little keys up here, it doesn't really like that just because I have this asterisk. So what I can do is I can format paint. So I like this formatting, nearest whole number. I'm just going to go to my little paintbrush and highlight. All right, now let's take an average. Actually, I can just carry this across. Okay, so it looks like my non-overhead athletes had better mean improvement, but that wasn't the question. The question was it significant? So I need to run a t-test. So let's say OH versus non-OH. Okay, so equals t.test. So select your first array, the overhead athlete, percent change, array 2, the non-overhead athlete. So it's 2 tails, and we're doing a independent samples t-test because we're comparing 2 different groups. So we're comparing the overhead athletes and the non-overhead athletes. And so the formula for that is your array 1, array 2, 2 tails, so 2, and then the type of test is 2. Okay, so look up here, make sure that looks right. And all right, so alpha, the default alpha value is 0.05. So our t-test p-value reported, our t-test gave us a p-value of greater than 0.05 and a p-value of 0.32. Okay, so not significant as far as overhead versus non-overhead athletes and change pre to post. So the next question is the average score for practice trials for only the right-handed participants. So I have my data nice and organized here. So basically what I could do is just make a new table, actually. So I'm going to say that this is going to be the mean practice. I'm just going to say mean. And then I'm going to copy these here in the same order, just in case I do want to make a graph with my pre and post values. For instance, in your lab, you're going to be required to do that. But then if I take the average of the right-handed participants for each one, so the average for practice trial 1 for everybody, the average practice trial 2 for, so let's see, here's my right-handeds, and select, there we go, and just carry it over. Okay, make sure to check your work, make sure that you got practice 2, which is the J column, and that only the right-handed participants are selected, so rows 10 through 16, looks good, then it should be K, 10 through 16, L, there we go. All right, so the average score for practice trials for the right-handed participants, and then if I were to just go ahead and take the average of all of this, just do this down here. Oop. Well, yes, that was a very, I understand. Oh gosh, okay, escape. Escape. All right, so the average for all 5 practice trials for the right-handed participants was 3.0. Right, and then I asked the average post score for all of the right-handed participants. So then if I just carry this, because it's just going to click right over to my post score, and then was 2.7. So your data set might be even closer than that, but that's pretty close. All right. So one thing for your lab, actually I'm going to keep that you might want to do, you're going to have to do line graphs. Okay, and basically what I did there is I just copied the formula and put it over here so that the right-handed, so H 10 through 16 was averaged. Okay, so I get that value. But then if you wanted to just insert your line graph so that you could kind of look at how they did pre, how they did post, as well as their practice trials, was there sort of percent improvement as they progressed through the practice trials, you can quickly just look at this line chart. Ooh, never mind. I don't like that. That's ugly. Here we go. Okay, so we see this nice performance curve, right? We see lots of increases up front, and then sort of so this would be a negatively accelerating curve. And of course, if we changed our axis a little bit, got rid of some of this white space, chances are it would show even a prettier, even smoother curve. But we can see here's our pre-value, and here's our post value, and there was an improvement from pre to post. So we can say that some learning did occur. And of course, you want to get rid of that because it's ugly. Okay. All right, so that's how you would make your graph for your lab report. Don't necessarily need that for your online assessment. All right, and the last question was, is there a significant difference that bilateral transfer occurred in this experiment? So this is a different type of t-test. So we were comparing our left-handed individuals and right-handed individuals. So that would have been 2 distinct groups, or overhead versus non-overhead athletes. Now, essentially, this is all of our participants pre and post. And so we're going to want to run a paired samples t-test, meaning that the participants in the first group are the same participants that, the participants that conducted, the pre are the same participants that conducted the post. So for this, I'm just going to write this right here. I'm just going to say pre versus post and equals t.test. So let's look at all of the pre-scores. That's my array 1. And then array 2 is all of my post scores. 2 tails always. And then this type of test is a paired sample. So 1 and then enter. And so this is definitely less than our alpha level of 0.05. We have a p-value of 0.002. So therefore, there is a significant difference between the pre and post trials. So we know that something definitely did occur. Right, so if you have any questions, please email me. And if not, I will see you in class soon. Thanks.